Alright, so this video is meant to more or less be a supplement to the code along I did for the depth first search implementation. And I'll also be trying to very quickly go over breadth first search as well. So I think these two graph traversal algorithms are very important to know. If you'd like, I can just make a GitHub repo and just put all of these implementations there so you can easily access it as well. Yeah, I think that will be quite helpful to you guys. Alright, so let's go over the depth first search implementation I did in that other video. I really wasn't in a talking mode, to be honest, then, so I'll just go it over here. And yeah, let me get my drawings. Okay, not this. Here we go. So in this one, I just chose to put the linked list implementation into a header file and link it to our depth first search implementation. I also had a make file. So if you don't want to do all of that, feel free to just implement the insert head, remove head, and have your node structure as well defined up here, right? Or you can just keep coding underneath the linked list implementation you have, whatever you find more comfortable. So let's start off with the structure of the graph, right? This is the most important thing when you're starting to work with graphs. You need to be able to encode your graph, right? So what you'll need is a number of vertices, and you'll need what's called an adjacency matrix. If you don't know what an adjacency matrix is, I'll do a quick explanation here, but again, as I always say, this sort of information, you can find so many good resources already on the internet. And so if you don't understand here, just go do some more digging and you should be fine. So let's say we had node, let's stick to the convention we have it in the program. So we'll say node 0, right? And we'll call this node 1, and we'll call this node 2. 1 points to 2, 2 points to 0, and then a 0 also points to node 3. Suppose this is the graph that we have, right? And we want to be able to traverse all the nodes in this graph. And why would you want to traverse all the nodes in the graph, right? Obviously, there's so many different applications. You could do things like pathfinding and finding the distance between two nodes and things like that, right? You can also do some pretty neat stuff like maze generation. Lots and lots of applications. It's such a cornerstone algorithm to know. Okay, so what is the adjacency matrix? Okay, so it looks something like this, right? 0, 1, 2, 3, 0, 1, 2, 3. So suppose this is our matrix here, right? Every single row inside of your matrix, so I'll write this down here. Row, right, corresponds to nodes, right? So think of a row as your current node that you're at. All right, corresponds to current node then. All right, so I hope that's clear enough. So we'll say node 0, right? Row 0, or row 1, row 0, okay? Will correspond to node 0. And the columns, right? The columns will encode the edges, okay? That's all it is. So if you look carefully, you'll say row 0, right? Is it connected to itself? No. Is it so you put a 0 here, right? Then you ask, is it connected to 1, to node 1? Yes, it is. So you put a 1 here. Connected to node 2? It isn't. Connected to node 3? It is. Okay. And node 1 is only connected to node 2, so 0 everywhere else. Node 2 is only connected to node 0, so 1 here and 0 everywhere else. And node 3, if you look, it's not connected to anything at all, so you just have zeros everywhere, okay? And so this is the adjacency matrix, and if you look, it's an n by n matrix. It's a square matrix. If you've ever taken linear algebra before, you know those have some very special properties, and I highly recommend, actually, if you get some time over December or whatever, whenever you just get some time to just study linear algebra, look up MIT OpenCourseware. Gilbert Strang just has an amazing course on linear algebra, and if you're interested in graph theory or you just want to get a little start on it, I think it's somewhere around lecture 11 or 12. He'll get into network analysis, and you'll really start to learn some powerful techniques. So, okay. So you know what the adjacency matrix is now, and why is it it's a double pointer here, right? Like, why though? So you'll see here, we have a function that creates the graph, right? And so what it's gonna do is, okay, this should be fairly stock standard to you by now. This line of code I shouldn't have to explain. And a new graph dot vertex number equals to vertex number. That's clear as well. Now here is where I think you might get a little bit confused. So new graph dot adjacency matrix, right? It's expecting a double pointer, so we use malloc, right, to dynamically generate some memory, and we'll cast it to the return type that it's expecting. Okay, this bit you shouldn't have to guess around. Here is where it might get a bit confusing for you. So we're doing vertex number times size of integer star. So what this means, right, it's going to allocate integer pointer times the amount of vertices that we have, right, inside of the node, or the amount of nodes we have inside of our graph, right? So it's just, if you'd like to think of it as an array of pointer values, okay? That's all it is, pretty much. An array of pointer values. So it'll look something like this. Where's my highlighter? It'll look something like this. So we'll have 0, 1, 2, and 3, right? Chunks of memory allocated by malloc that are going to be pointers, okay? And so that's all it is, really. Nothing too special here, right? So, but they're expecting something, some value, right? They're expecting some value. And so what we have to do next is that we'll iterate, right? We'll iterate over this array now, okay? And what we're going to do is we're going to dereference, right? We'll dereference the array, and I hope you know what this dereference operator does to an array. This bit of code here by itself is going to take us to the first element inside of that array, right? I hope you know this. And the plus I now is where the dynamism comes in, that because we're iterating over the array. So on the first bout, right, it's just going to be 0, so it's irrelevant. And so this bit is going to matter, and that'll be the first pointer, right, element inside of the array. And then it'll say integer star C allocate. C allocate stands for contiguous allocation, and contiguous allocations means that the memory is being allocated side by side, which is quite literally the definition of an array, right? And it takes two parameters, the vertex number and well, not vertex number, but the number of I suppose elements, you can say, you want side by side next to each other, for lack of a better word. I hope I'm getting the point across. And the size, right, of the elements themselves. And so what we're going to be doing is allocating memory for an array, pretty much, right? We're basically generating an array here. And it's going to be size of vertex number, so the amount of nodes we have. And it's going to be of type integer, right? And we're typecasting it to integer pointer, okay? Because remember that it's coming here, right? So, and this is a pointer. This is expecting a pointer value. So this pointer value is going to be pointing to this array that's going to be contiguously allocated. And so it's going to look like this. Then it's going to return a chunk of memory, right? So you can say it's returning an array with 4 elements, with size enough for 4 elements. 0, 1, 2, and 3. All right, so that's what it's going to look like here. And so now already, if you're paying attention, we have an n by n matrix here that's forming, right? I hope you're starting to see that. And the same thing is going to happen here, the same thing is going to happen here, and the same thing is going to happen here. So you'll have 4 here, 4 here, 4 here, and 4 here. And so I think I can draw this a little bit better. So initially, right, initially, oops, let me draw it like this. I'll change to how the bracket is, so maybe you can get, so initially we're going to allocate, let's say we have 4 nodes, right? We're going to allocate an array with pointers, right? So there's nothing here, there's nothing here, there's nothing here, there's nothing here, right? Because we just allocated that here. And then what we're going to do is that we're going to iterate over this array, right? And we're going to say, okay, for this first pointer here, right, we're going to give it a pointer to an array, right? And that array is going to be this here, which calloc is going to return, right? And so we can say, so this is now going to be 0, 1, 2, 3, right? And then the same thing here, and the same thing here. Okay, 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. And so it's an n by n matrix. Can you see that? Right? And how do we access values inside of this matrix? Well, all you have to do, right, is, so say for instance we wanted to access the first element here, this 0, right? What you do is you dereference the, so let's see what's the, it's the graph, right? So whatever your graph name is, and we use like new graph, but your graph name can be anything. New graph, the adjacency matrix, right? What this is going to do, as I was explaining previously here, is going to give you, return the first element here, right? And then you have to dereference again. So you wrap this in quotes and you dereference again, right? Because you can do that. Because it has a, this is an array inside of here. So now you're here, right? You're inside of this first bucket, if you want to call it a bucket. They call it buckets for some reason, especially in hash tables. So now you're here. And now you want to get access to this array. Well, if you dereference it again, right, it's going to give you access by default to the first element inside of that array. I hope you understand. So that's how we get access to 0. If we wanted access to 2, what would we do? Well, okay, we still need access to the first bucket, but now it has to be, instead of just access to this, it has to be +2, right? +1, +2. So +2. There we go. And it would give us access to 2, right? All right, so I hope that was sufficiently well explained, and I won't have to explain it again. But if it wasn't well explained, feel free to just try another method or an easier method. And this is obviously using dynamic memory allocation. A lot of tutorials I think you see online use arrays, which are much beginner friendly, I think. But this is just a proper way, I'd say, to implement a graph traversal algorithm. I don't see any downsides to doing this, and just upsides. So of course feel free to correct me on that if you know better. All right, so void add edge. What is this doing? So this is just a function to encode that adjacency matrix. Oh, and by the way, callocate is going to set the values inside of here to 0 by default. So this is going to be 0, this is going to be 0, this is going to be 0, and this is going to be 0, right? So the entire square matrix is just going to be populated with zeros, okay, by default. And then, as we were explaining previously, we have this graph structure here, right? And we have to encode it into our adjacency matrix. And we already know how to access these elements, right? So all we have to do is access this element and change it to 1, right? That's all we have to do. So in order to encode the adjacency matrix. So that's what we're doing here, essentially. We have a function called add edge. It's going to take the graph structure, it's going to take the source node and the destination node. So the source node would be the row and the destination node would be the column, right? And so again, as I was explaining, the first thing you do is you dereference here, right? And so this is going to give you the source node, right? Plus source node, as you can see. And then, so this gives you the row, right? And then you dereference again, and you add the destination node, right? So you add the edge that it's connecting to, and you set it equal to 1. Okay? I hope that's that's clear enough. So yeah, that's how you encode the adjacency matrix. Now for the depth first search implementation itself, so let me see, why do I have another console open here? I don't know. Let me scroll down to the bottom, or actually I can do it right here at the top. I don't see why not. I'll just erase our little adjacency matrix here, make a bit of space. Okay, this is gone. All right, how does depth first search work, and what's going on here? So I'll use blue. I think blue just looks nice. So what you're going to need, right, if you look at our function definition here, we need the graph itself, obviously, and we need the starting vertex, right? So suppose that our starting vertex was 0, okay? Suppose that it was 0. What's going to happen? Well, what the depth first search algorithm needs, right? It needs a couple of things. First of all, it needs to know the nodes. Obviously, you can think of this yourself as well. You need to know the nodes that you visited, right? So you don't, visit the same node twice. That wouldn't be good. And you need a stack data structure, right? And I think by now everybody should be familiar with what the stack data structure is. It's just a linked list, right? And all you're doing is you're adding to the head of the linked list and you're removing from the head of the linked list. And that's like the push and the pop operation, right? And it works on the last in, first out principle. Okay, and so you'll get to see how the stack is used here in the depth first search. But okay, you come here, right? And you mark this node as visited, right? And then you check, right? You start to check all of the neighboring nodes. So you check the first neighboring node here, right? And you come over here. And if you find something, you find an unvisited neighboring node, right? Then you push this node onto the stack, pretty much, all right? And then you mark it as visited, right? And then you do the same thing again. You check for an unvisited node, right? And in this case, there is an unvisited node here. So you come over here and you push 2 onto the stack, right? And let me write what the stack is looking like. So the stack started off as 0 to null, right? And then we pushed 1 onto the stack. And now we're pushing 2 onto the stack. And then we're going to check, okay, is there an unvisited node, right? So it's going to check. It's going to see, okay, yeah, there is a connection here to 0, but it's already been visited. And there's nowhere else for me to go. And so what it's going to do is that it's going to remove 2 off of the stack, right? And then it's going to come to 1. And it's going to check again, okay, is there an unvisited node, right? And it's going to come here and say, okay, well, there's 2 here, but it's not, we've already visited it. So, okay, we'll pop 1 off of the stack, right? And then it's going to come here to 0 and it's going to ask the same question. It's going to come here back to node 1, right? And it's going to see that it's, it's an edge, but it's going to see that it's also been visited. So it's going to say, okay, let's not bother with that. Let's keep checking, right? And it's going to come here and it's going to see, okay, no tree. We haven't visited this. So we'll put no tree onto the stack, right? And we'll mark it as visited. And so now this has been marked as visited. And then it's going to grab, and it's going to come here and say, okay, it's going to grab the current head of the stack, right? And then it's going to, that's what it's doing at the start, actually. It's grabbing the current head and it's checking the edges. It's going to say, okay, well, actually, no tree has no edges whatsoever. So just pop it off of the stack, and then it's going to come back here to node 0. And it's going to say, okay, well, node 1, no tree, unvisited. There are no other connections anywhere. Pop it off of the stack. And then finally, your stack or your linked list is just going to be empty. And that's how you know that you've traversed the entire graph, okay? And so I hope I didn't give you a terrible, long-winded explanation of a rather simple algorithm. And of course, if I did, feel free to, YouTube University your way out of this one. So let's go through that with our implementation here that we did, and yeah, you'll see for yourself how. And I'm not gonna go over the print adjacent function. You should be able to implement this on your own. And yeah, I remember during the actual live coding, There was a typo here with the II, right? I was literally just like, I was so confused, right? I was like, there's no way that this should not be working, right? Yeah, but there was a typo here, and it was so hard to see because it's I, right? That I was just like skimming over the thing so fast every time. And then I was like, okay, let me just like look at it carefully now. And eventually I did see the II. But that took me a while to actually find. So I was like, yeah, that was very sus. Okay, so we said that we needed a way to keep track of the visited nodes, right? And so what we're going to do is we'll have an integer pointer called visited, and it's going to be an array, right? And we're going to use callocate again. And remember, callocate is going to take the number of elements and the size of the elements, right? And so since it's an array, right, remember the first element of an array, or if you dereference an array, right, the first element is just a pointer, right? That's basically it. So I hope you understand how arrays work. If you don't, I feel as though you're going to have a bit of a hard time following along with these implementations. But okay, it's a pointer, right, to this array here. And yeah, that's all it is. It's an array, if you want to think of it that way. And we initialize the stack to null, and then as we said, we put the head onto the stack, right? We insert head to give it the stack, and we give it start vertex. Start vertex in this case is just the data that we're giving to the stack. In this case, our node implementation is taking a data, and it's just having the next pointer, right? So that's all it is. So start vertex is, in this case, is the data that we're giving to the node. And so again, while the stack is not equal to null, right? So you get the current vertex. Whoa, my voice is breaking up. So you get the current vertex, and you say stack.data, right? So integer current vertex is equal to stack.data. So we're grabbing the current vertex at the start every single time, right? And you check now, right? You say visited, right? Star visited is going to give you the first element inside of your array, which is what I was trying to explain up here, right? So, but what we want to know is the current vertex been visited? So we just add current vertex to it, right? So when we start with 0, right, it's going to say star visited plus 0 because current vertex is going to be 0, right? Remember, we gave 0 here. 0 is the starting vertex to this function. And that's what's being passed in as the data to the node structure, right? So stack.data is going to just pull that out and put it in here. So it'll be 0 plus visited. So it's going to check the first element, right, which corresponds to node 0. And all right, it's going to be 0 because remember, calloc automatically just populates your array with zeros. And it's going to say, okay, so if not visited, right? So it's already 0. So this here is going to evaluate to false, and then the not operator is going to flip it to true, right? And so it's going to evaluate to true, and then it's going to come down here and it's going to set it equal to 1. So it'll mark it as visited, okay? And then what we do is we're going to explore the neighboring nodes, right? And so, yeah, to explore the neighboring nodes, all you have to do is iterate over the particular node. So yeah, if you look very carefully, so you'll say for I, integer I equals 0, I is less than graph dot vertex number, so it's just for I plus plus, okay? And so what you're gonna do is, already this seems, I think, fairly straightforward actually. So you should be guessing that this is going to just give you the node, right? The current node that you're at. And then you add the current vertex to it. Okay? And remember, current vertex is defined up here, right? We're pulling the current vertex off of the stack, the head of the stack. So in this case, current vertex is going to be 0, right? On this iteration example that we're going over, current vertex is going to be 0. Right, so it's going to grab the 0th row, if you want to say, right? And then it's going to iterate. So every single time, it's just the 0th row, right? But the only thing that's changing is going to be I. So we're going across now the array that you know, going across now. So basically just moving across the row. That's what this is doing. And so it's going to check then. It's checking all the edges, right? This is how you check all the edges. And then you'll say, okay, well, if there's an edge encoded here, right, that's essentially, it's going to either be a 0 or a 1 that's going to be returned here. So if it's a 1, that means there's an edge there, right, at position I. And if it hasn't been visited, as I was explaining in the algorithm, then what I do is I use the flag variable here, right? I set flag equal to I, right, as a way to store the information or the node that it's connected to, and I break out. Immediately, I just break out. And so if you notice here as well, flag is always being reset to -1 here, right? And then it's going to come down here and it's going to check. Okay, so as long as the flag is not -1, right? So if the flag was -1, it means that this bit of code here ran, right? And it didn't find anything. Okay, it didn't find anything. It didn't break out here. So it didn't find anything. And it wasn't able to reset that flag variable at all. And so that just means that there's no edges, and you know, it wasn't able to find an edge that's not visited. And so yeah, however, if it was able to find an edge that was visited, you pop it onto the stack like I was explaining, push the node onto the stack. Otherwise, you just pop it off of the stack, right? And then the algorithm is going to go all the way up to here again, and it's going to grab the current head from the stack, right? So in this case, when we started at 0, right, it's going to go to 1, right? And then it pushed 1 onto the stack, right? And then it came all the way up here again, and then it's going to grab the 1 from the stack here, right? And then it's going to check, oh, mark that as visited, set the flag to -1, check all the edges, right? Check if it's been visited or not. And then it's going to say, oh yeah, well, there's an unvisited edge here, node, which is 2. Then it's going to say, okay, well, you know, go ahead and insert that onto the stack. 2 gets inserted onto the stack. And then you come up here again, right? And you grab the current head off, the data off of the current head, which is now 2. You do the same thing again. You see, oh, well, actually, there's an unvisited node. Or rather, there isn't any nodes that we haven't visited because 0 has already been marked as visited. So in this case, this is not going to run. And so you pop 2 off of the stack, you pop 1 off of the stack, and then you end up at 0. And then 0 gets put into current vertex, and then it's going to reach here again. It's going to come to, so this is how it's going to work, right? It's going to go here, and then it's going to say, okay, nope. And then it's going to come here to 1, and it's going to see that there's something encoded here, right? And inside of, if you can imagine what's going on in the adjacency matrix, right? And then it's going to check tree, right? And that's how it's going to see, okay, well, it's going to check 2, actually. It's going to see a 0 here. And it's going to say, okay, well, nope, keep going. And then it's going to, at the last iteration, right? And so it's actually, the adjacency matrix for this was, let's see, 0, 0, 0. So it's just connected to 1, 0, 1, 0, 1, right? So as we're iterating across, right, this array here, it's going to check here, 0, nah, it's going to check here. It's going to evaluate to true, right? But the entire expression is going to evaluate to false because of this AND statement here. So it's also checking for the visiting condition, which is important, right? So it's going to come here and it's going to say, okay, well, yeah, the edge exists, right? But it's already been visited. Keep going. It's going to come here. It's going to see a 0. It's going to automatically evaluate to false. It's going to come here, and then it's finally going to see a 1, which is the tree, corresponding to the tree, right? And by now we're at I equals tree, right? We're at I equals tree here. And then it's going to say, okay, it hasn't been visited. And so we know that node tree then is the node we need to store in our flag. And as you can see, we're inserting that flag into the head. And the algorithm just continues onwards, okay? So yeah, that's it for depth first search. And I hope that was clear. There wasn't too terrible of an explanation. The next one I want to just very quickly cover. Let me check the time. Yeah, I think I've got like maybe 10 minutes or something to try and get this out of the way. Let me quit out of here. Yeah, prep for a search. And yeah, Well, this one I did the lazy implementation I was telling you about, where you can just code under the linked list. And yeah, there's not a problem with that either. So let's go over what breadth first search is. So again, already you're seeing the same graph structure, and you're going to be reusing these patterns over and over again, just in a slightly different algorithm, slightly different data structures. But you know, by and far, it's the same set of patterns once you learn them. Once you understand what this double pointer represents, I think you're good to go then. Right? And so, okay, so again, the graph star is going to do the same thing, right? Same thing again we're doing here. I'm not going to spend any time explaining what this is doing. Okay, you should already know that we're just creating our adjacency matrix and populating it with zeros, right? That's all this is doing. Then the add edge function, again, same thing. All we're doing now is, this is just a way for us to encode our adjacency matrix, a function, because it's just all zeros. And we'll encode the adjacency matrix. And then this is the breadth first search algorithm here. Okay. So maybe I should just use the example that I have here. And so I'll try to draw this graph out. Insert page after, yay. Alright, so we have one node here. Right, and so you should know as well that a breadth first search is actually ideally suited for traversing tree type structures, right? Obviously, you can interchange them and use whatever you want. They're all just graphs at the end of the day, right? So depth first search would be perfectly, you could use that in a tree if you'd like as well, but I personally think just breadth first search is just way more suited for traversing a tree, and you'll see why. So we have a parent node up top here, right? We can see like 0, 0, 0, right? And 0 connects to node 1. So it has 3 child nodes. So there's one parent node and there's 3 child nodes. So this is 0, 1, 2, and 3. Yep. And so let's see. 2 connects to 4, I think, yeah. 4, oh, so 2 actually connects to 2 more. It has 2 child nodes. So 4 and 5. And then 5 connects to 6, like this. 6. Oh my god, my drawing is so terrible. 5 connects to 6 like this. Okay. So yeah, I think this is our graph that the adjacency matrix is trying to encode. And so the adjacency matrix, instead of using a stack, it uses a queue, right? If you don't know what a queue is, let me just take like 2 seconds to explain that very quickly. So it's just a linked list. Again, it's all just linked lists. And so imagine this was our queue here, right? So all you're doing with a queue is that there are 2 operations, in queue and dequeue, right? And when you're in queuing, I think you're adding to the tail. Yeah, I think so. Yeah, that's what you're doing. So let's see. Suppose that our linked list started off as empty, right? And we put an item in. We in-queued something in, right? Then we add it to the tail. So this would just be here, and we have an add tail function, right? And then so this would be, let's say this is 1, right? 1 or 0. Let's say this is 0. And then now we in-queued something else. Then we're adding it to the tail again, right? Which means we're inserting it at this position, right? So 0 would now move up here, and this would be the new node that we added in, which would be 1. Fairly simple, I think, right? And you just keep adding stuff to the tail. That's how you in-queue, right? And then dequeue is you just remove from the head, pretty much. Remove from the head. So it's, I think this is a first in, first out principle, right? So the first element in, if you realize, is always going to be this 0, right? If we keep adding to the tail, in-queuing to the tail, right? And then when we dequeue, right, we just remove from the head. So the first element in would be the first element out, essentially. So that's what the queue data structure is doing. All right, so let's see. Yeah, so we have to just now very quickly explain what this breadth first search algorithm is going to do. So we have, again, keeping track of what we have visited, we set this equal to null, right? We insert the tail, which is the NQ operation, right? I think this pattern should already start to be, you know, familiar to you from when we were using the stack from the last time. It's the same, you know, the same idea, I think. And then we'll say while the queue is not equal to null, right? Then you check, again, it's the same thing. You check if it's been visited, right? And you mark it as visited. And here I was just printing the queue data out. And now here, if you pay close attention, right? So it's the same thing again. We're traversing down the array, right? And we're going to say, okay, the first thing we're going to do is we're going to get the queue.data. In this particular case, this would be the current node, or the current vertex. Queue.data is the current vertex. Whoops. Let me just, there we go. So that would be the current vertex. So the last time I put that, I just put that inside of, I just grabbed the current and put it inside of a node. We were able to access it there, but okay. And then we just add I, right? And so it's literally the same line of code as the last time, right? And then, but now all we're going to do is we're going to add it to the tail then, right? Otherwise, we just delete the queue. So let's try to run through this algorithm on this breadth first search tree and see what's going to happen, right? So let's start at 0. So let's say we selected node 0. And so it's going to put it into the queue, right? 0 is going to be put into the queue. And then it's going to mark it as visited, right? And then it's going to check now across for all the edges, essentially, right? It's going to check for all the edges that we haven't visited. And this is going to do it in one go. If you remember in the last time, we were breaking out, in the depth first search algorithm, we were breaking out as soon as we found a match, right? And so that's why we were able to traverse pretty much the depth of the graph, right? So if we use depth first search here, it would go boop, 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 and it would find the deepest node. Quite literally, the deepest node is going to find it, and it's going to backtrack its way up. What breadth first search, though, is going to do is instead of break out straight away, it's going to come here and it's going to say, okay, there's a node here, there's a node here, there's a node here, right? All the edges are going to be added to the queue, pretty much. So it's going to say, okay, it's going to come here and it's going to find a 1, right? And it's going to say, okay, well, you know, there's a 1 here, so let's add that to the queue. So there's a 1 here, let's add that to the tail, right? Then it's going to find a 2 and it's going to say, okay, well, let's add that to the queue. And it's going to find a 3, it's going to do pretty much the same thing. Add this to the queue as well. And it's marking them as red. So it's not marking them as red quite yet. So what it's going to do then is, yeah, so it NQ'd all of these, came here, and then you pop the head off, yeah. So I don't know why I did this. It doesn't seem entirely intuitive to me, but okay, it works, I suppose. So yeah, you DQ the head that you're currently at. DQ the head, and yeah, so now 1 becomes your new head. All right, so we're here, and then the program is going to come up all the way back to the top of the loop. Let me make sure, where's this loop going? Yeah, so we are deleting the head every single time. Just wanted to clarify that. And so yeah, as I said though in my hash table tutorial, every single time I implement data structure, it's going to be done slightly differently, but sometimes my brain is just functioning slightly better than other times, and so I might implement something that's super duper optimized, and then another time you'll just see a really scuffed implementation. So I think this is just one of those highly optimized applications. So okay, it's gonna come up here, and it's gonna check if it's visited, right? The current node q.data is gonna check if it's visited or not, right? That's the current head, right? And it's gonna see here that okay, it hasn't been visited. Mark it as visited, right? And then again, do the same thing here, right? Check all the cases, and see if we have basically loop through it and see if there's any edges. So if there are no edges, then great. We can go ahead and remove this, delete this off of the head of the queue, right? And then it's gonna come up here again, and it's gonna check 2, right? And we're going to see that there are actually 2 edges, so there's 4 and there's 5. And so we're going to enqueue those, right? We're going to add those to the queue. So here we're going to add 4, and we're going to add 5. And then it's going to come down here, and it's going to remove this 2 off of the queue. Yeah, well, yeah, now this algorithm just makes a lot of sense to me. Yeah. All right, and then, so we're at 4 and 5, right? Then it's going to come up here again, and it's going to grab the head, right? And so it's just going to check, okay, has it already been visited, which is the current head, and we'll just mark it as visited. If not, and then it's going to come down here, and it's going to say, okay, any edges, right? No edges. Great. Remove this from the stack. Same thing with 4. It's going to come, do the same thing, remove 4. Then it's going to get to 5, right? And it's going to say, okay, well, yeah, 5 is connected to 6. So add 6 to the tail, right? And then remove 5. Then it's going to mark 6 as red, or mark it as processed, whatever you want to call it. And then, again, the algorithm is just going to do its thing, and eventually it'll say 6 does not have any neighbors. We can go ahead and delete that. And finally, the queue is empty, right? And so that's how we know we've completed our breadth first search algorithm. And so, yeah. So if you notice, the key difference, though, is the breadth first search is searching by levels, right? So it started with this level, and then it went to this level, and then it went to this level here, right? And so this sort of thing, if you can think of it like if this was a file structure, right, /home /etc /something, and you just wanted to find some file here, right, that was in this directory here, you can just very quickly search on this level, right? And you don't have to use the depth first search, which might take you all the way down here to 6 or something like that. And so I hope you're starting to see how these types of algorithms might be, and data structures might be useful. And feel free to do some more fun exercises on your own. You can try to find some pathfinding algorithms and try to come up with some little problems and how you can apply this. But I hope this little tutorial was somewhat helpful to you. And yeah, have a good day, guys. Now I'm about to go start mine.